Alright, hello everyone and welcome again. So we have been talking about how to find the area between given two curves, okay? So we came across relatively simple questions. I think we solved like 4 problems over the last 2 videos. So now we are going to take a different turn, okay? So we are going to look at some challenging, or not necessarily challenging, but different problems in this category. So before we do that, I want you to look at some of the problems that we solved. Okay, I want you to look at them again. So remember, I think in the first video we solved a problem where you had to find the area like here in between these two graphs. So then there was another problem in the second video there where the area looked like these two second and third graph. Right, now why am I showing this to you again? Now check this out. I'm going to do a small experiment. Now think about this. If I draw several vertical lines in between these two graphs, in between each of these graphs, okay, in each of these graphs, yeah, between the curves, okay, at several points, something you might notice is that the touching points of these vertical lines from above and bottom, they are always between the same function. Okay, think about this. I think so here this function, if this is like 8x minus x square, if this is like x square, so always these two lines are between these two functions. That's what I'm trying to say. Okay, so here also the topmost part is the curve part and the bottom part, they are touching the line. Same here, curve and line, curve and line. Here I think this curve was e to the x, this curve was square root x in the problems that we saw last video. So again, top part in these lines always touching e to the x, bottom part of these vertical lines always touching square root x. That means what I'm trying to say here is that this region, it does not change the shape. It's always between the same two curves. Okay, that's the idea. Now to understand this better, I will show you a different example. Think about your finding the area highlighted by this green color region. Now think about this. Now in this green color region, the region that I highlighted from green, do you see that these regions are always between the same two curves? Or do you see multiple regions within this entire region? Think about this. Now let's do that test. Let's draw some vertical lines. I'm going to only draw 2. Check this out. This vertical line from top touches square root x square, square root x plus 2. On bottom it touches the x-axis. But here from top, yes, still it touches square root x plus 2. But from bottom it touches y is equal to x, this straight line. Now you can all of a sudden see that the area changed. That means the region changed in the sense that they are not always between the same two functions or regions or boundaries. Okay, anyway you want to think about it. So you can think this entire region is composed of 2 different shapes. That's the idea. Okay, it's equivalent to a problem like this. Think about this. In high school, you might have come across these problems, math problems, that you have to find the area of this shape. So here the problem is you have half a circle, that's a different shape, and then you have a rectangle, right? So the shapes change within the entire region. That's what's exactly happening here, right? So if you try to write area between these two curves as from -2 to 2, because x going from -2 to 2, and like we learned in the last video, square root x plus 2, that's the function on the top, and the function on the bottom, if you think it like x, and if you try to find the area using this setup like we learned in the last video, it's not going to work out. Okay, because our region, entire region is made out of multiple regions. Now how do you solve this problem? There are a couple of ways. I'm going to show you both, one way in this video, the other way in the next video. Right, here's the first idea. Just like this problem, if you want to find the area of this entire region, what would you do? You find the area of the circular region separately and then the rectangle separately, and then add them up. A simple geometric problem, right? We are going to do the same here. We are going to identify the multiple regions, separate them out. Now, if you look carefully, these two regions separated out by the y-axis. Here's the first region. Here's the second region, right? So I'm going to delete these, red lines. So the first region is the part where I highlighted by green. The second region is the part that I highlight by the purple color. Okay. Now I can come up with two integrals to represent the area of these two regions separately and then add them up. That's the idea. So first region area will be given by, so this is 0. So you are integrating from -2 to 0. Between which curves? Between square root x plus 2 and x-axis, right? So it's basically asking you to find the area under square root x plus 2. So this is it. That's the integral. That integral will give you the area of the region 1. Okay. Plus the second region area is going from 0 to 2, right? 0 to 2 between what? Between square root x plus 2, that's what's on the top, minus x, right? That's the function on the bottom. Right here I could say minus 0 because it's x-axis, x is equal to 0, but it doesn't matter, right? Subtracting by 0, it doesn't matter. So that's why I didn't do that in the first region. So yeah, this is what will give you the area of the entire region. Okay, now this is important. This is a little bit different from the problems that we solved in the last two videos. Okay, the problems that we solved in the last two videos were very simple problems. So now let's go ahead and integrate these two. So square root x plus 2, I'm going to write it as x plus 2 to the half, plus 0 to 2 here, x plus 2 to the half minus 6. Now let's integrate x plus 2 to the half. It's x plus 2 to the half plus 1 over half plus 1. You are going from -2 to 0 plus here. If you integrate x plus 2 to the half plus 1 over half plus 1 minus x, it's x square over 2. So you're going from 0 to 2. Now if you simplify this, this is x plus 2 to the 3 over 2, 2 over 3. Okay, and 0 -2 plus here x plus 2 to the 3 over 2 times 2 over 3 minus x square over 2, going from 0 to 2. So now let's substitute. So if you substitute 0, 0 plus 2 is 2. So it's 2 over 3, 2 to the 3 over 2 minus, now substitute -2. 2 plus -2 is 0. So this is 0. Plus, now substitute 2 here. So 2 plus 2 is 4. So 2 times 4 to the 3 over 2 over 3 minus 2 square is 4. 4 over 2 is 2. And then from here subtract what you get by plugging 0. So if you substitute 0, 0 plus 2 is 2. So 2 to the 3 over 2 over 3. If you substitute 0 here, it's 0. So this is 2 to the 3 over 2 over 3 plus 2 times 4 to the 3 over 2 over 3 minus 2 here minus 2 to the 3 over 2 over 3. So these two cancels out. And here let's see what we get. 2 times 4. So this is 4 to the half to the third power. That's 3 over 2. That's how we interpret, right? 4 to the half means square root of 4, which is 2. So it's 2 times 2 cube. Then if this is 2, 2 cube is 8 over 3 minus 2. No, there's no 2 here, right? Yeah. So it's 16 over 3 minus 2 through 2. So that means this is 10 over 3. So this is unit squares 10 over 3. So that's the area of this region. Okay, so this is different. Now we had to deal with multiple regions within our entire region. So we break it up into multiple regions and then set up several integrals and then add all the answers. That's the idea. Okay, right. So that's one way to solve these type of problems. Okay, so I'm going to teach you another way to solve these type of problems in the next video. Thank you.